Bluetooth. Get it straight.
Let's take a look at a sample problem for turbulent flow, and that means we're probably going to have to use the Moody diagram, or some other technique to iterate to get to our solution. But let's just take it from the top here. So we've got a pipe coming out of a tank here, and the tank is D in depth. There's a big D here for the diameter of the pipe. That's 75 millimeters. The pipe is long, so this is not drawn to scale, but the pipe is 100 meters long, and there's a square inlet to the pipe with a KL given. So this is telling us that we're going to have to look at the head loss for those by that shape there, as well as for the pipe. So we'll have two types of head loss here, one for the pipe and one for the inlet. Also given the flow rate, 0.01 cubic meters per second. So this is Bernoulli with major and minor losses. So we have, we take points 1 here, 2 at the end of the pipe here. As you would suspect, you would get the pressure at the top is 0 because that's atmospheric. The pressure, the velocity at the top is 0 because it's a full tank and it stays full, steady situation here. The Z1 is actually equal to the depth there, little d. At 2, pressure is also 0 because it's atmospheric. There is a velocity, so we keep that term. We could make Z2 the datum, so that goes away. And we have the head loss major and the head loss minor. So the depth of the tank that's causing that flow rate, that's what we're after, by the way, is V squared over 2G plus the major head loss plus the minor head loss. So let's first look at these head loss terms. So the major head loss term is this scales with the square of velocity and has this friction factor. So we know everything in here. We know L, we know D, but we don't know F. And the minor head loss is simple. That's just the velocity squared times this KL term that's given. So the problem is we don't know F and we don't know V2. So we've got two unknowns. But we do know that if we can figure them out, we'll have an easy expression for this depth of the tank. So V2 is pretty easy to get. We just take Q over A because they gave us the flow rate and we know the diameter of the pipe. So we do Q over A and we get 2.26 meters squared per second. With that, we can calculate a Reynolds number. The Reynolds number comes through like this. Made a little note here on the units of viscosity you could check out. But the Reynolds number, let's go down to the Moody diagram here. That's what I mean by the Moody diagram. So we enter the Moody diagram here, and our Reynolds number, about 1.7 times 10 to the 5th, and that shoots us over to around here, which is more or less 0.00045. So now we can, oops, this should be the value here. So the 0.00045 should go in there. And if you plug that all in together, you should come up with a depth of 0.55 meters. So this is just a reminder over here about the units, because the table says Newton seconds per meter squared, but Newton is a kilogram meter per second squared. So if you put it all together, you get these units here that work well in the Reynolds number. Just a little note there, because you may have some trouble getting your Reynolds number dimensionless, and we know it should be dimensionless. So that's an example of a turbulent flow problem where you didn't have to iterate because you pretty much were given the velocity here in terms of the flow rate, but you did have to use the Moody diagram to get the friction factor. So that's a turbulent example.